In this section, we're going to learn how to optimize functions in two variables f of x, y. So the function f of x, y is said to have a relative maximum at a point p equals ab, which we'll later call a critical point, in the domain of f, if the function at ab is greater than or equal to all of the other function values around that same area in a circular disk. That's what that's referring to. In the same region of the graph, this function value has got to be the biggest in order for this to be a maximum. The function f of xy is said to have a relative minimum at this point q, which we'll also call a critical point, in the domain of f if the function value at CD is less than or equal to the function value everywhere around that particular location. And that's going to be considered a circular disk centered at CD. The points P and Q, like I said, are going to be called the critical points. And so the picture you see is a graph in three-dimensional space. It's a function of f in terms of x and y. The relative maximum is labeled at the topmost section of the graph, and the relative minimum is at the bottom part of the graph. And you can see that the relative maximum is the highest of anywhere near that particular location, and the same as with the relative minimum. It's the lowest point in that particular region of the graph, in this particular region. So we need to remember how we went about finding critical points with two variables, with just x and y, and two-dimensional space. What was our process that we used to figure out critical points weeks ago during this semester? So if you think about it, if I gave you a function f of x, that's a graph in two-dimensional space, I asked you to find critical points, you would have said, well, let's take the derivative, set it equal to 0, and solve for x. So that's going to be how we did this in two-dimensional space. The same process is going to be used now in three-dimensional space, but now when we take a derivative, we have to identify which is the variable and which is going to be considered a constant or treated as a constant. And so we're going to be looking at partial derivatives. A point AB in the domain of f of xy for which the partial derivatives fx and fy both exist is called a critical point when fx at the output, or the input AB is equal to 0 and fy at AB is equal to 0. So those are both considered to be critical points, which is going to be a potential relative max or min of your graph. Back in college algebra, we learned how to solve a system of two equations with two variables. And if you'll notice, what we have up here is going to be a system of two equations with two variables. Your x and your y are your variables. And so we need to remember how we went about solving those types of systems back in college algebra, like Math 119 at ISU. So a couple methods that we discussed back in the day. We would have used the substitution method, or we probably would have used matrices, or some other options could have included the addition method, which is also called the elimination method. We're going to focus mostly on using substitution method in this class because I'm sure it's been a while since you've had to manipulate matrices. We're not going to teach that in this particular class, and so if you are pretty good with your matrix skills, feel free to use the row reduction, row operations on a matrix, and feel free to use your calculator. But that only works if your equations are linear. A lot of the times your system of equations will involve equations that are nonlinear, and then your only approach is to use the substitution method. And so that's going to be the one that I will focus on. I'll use the substitution method for the most part. Whatever solutions you get to your system of equations for x and y, those are going to be considered your critical points. All right, but you have to remember, just like back in two-dimensional space, not all critical points are going to be relative extreme, because sometimes if you've got a graph that looks like this, yeah, there's a critical point there and there's a critical point there, and those are both going to be relative extremes, max and min. But sometimes you'll have a function that may have a horizontal tangent line somewhere that is not a relative extreme. That is still going to be found as a critical point, but it is not a max or min. The same thing can happen in three-dimensional space. A relative max is shown in this first graph on the left. You can see that there's been a plane almost like a flat sheet of paper or something placed on top of your functions graph, and you can see that the plane, which is this part that I'm referring to, that plane is considered to be perpendicular to your vertical axis, which would be right here. And that's what makes that plane considered to be horizontal, right? So we can't talk about a horizontal line because now in three-dimensional space, that line has been made into a plane. And so if that plane is horizontal, which means perpendicular to your vertical axis, it's considered to be at a relative max or a relative min if it's on the bottom. Another case where you could have a critical point is shown in the graph in the middle. It looks like a saddle that you might put on a horse, and so that point that I've identified is called a saddle point. This is also going to be found as a critical point, but it is not a max or a min. And the third case that you might come across is a graph where you have an absolute minimum or an absolute max, but the process is identical to finding relative extreme points. And if anybody's curious on what graphs are going to look like that I ask you to manipulate and solve, you can use an online 3D grapher, Google 3D grapher, and you'll come up with lots of different options. One that is fairly simple to utilize is this geogebra.org/3D. That is a useful online tool for graphing in three-dimensional space. It's not required, that's just if you want to explore a little bit more. Okay, so once you find your critical points, you have to determine if they are maximum, minimum, or neither in the case of a saddle point. And so in order to do that, we're going to use what's called the second partials test. The second partials test is where you compute partial derivatives of your function that you're maximizing or minimizing, including second partial derivatives as well. And then you put things together in a way to form what we call the d-test formula. This d-test formula here in the middle of the page is going to be a formula that you'll need to know. So if you are working on accumulating like a note card to use on your next test, where you've got a lot of the important information right at your fingertips, that is a formula you would put on this note card to help you locate that for the test. So the d-test formula, or just the d formula if you want to call it that, is found by taking second partial derivatives of x and of y, multiplying them together, minus the mixed partials squared. So that is what makes up your d-test formula. Once again, you'll have to know that. The process to figure out if your critical points are relative min, max, or saddle point, that would be neither, is first of all, find those critical points, those A-B ordered pairs of your function, and we'll discuss how to do that. The next point says to figure out the output for D of AB. And so if you have multiple critical points, you're going to take each of those A, B values and plug them into your function D for X and Y. And then this next point says if D of AB is negative, that means that your critical point is a saddle point. If your D of AB is positive and the second partial derivative of x at AB is also positive, in other words, your function's concave up there, then we have a relative minimum. If D of AB is positive, but your second partial is negative at AB, that means your function's concave down. That means we have a relative maximum. And if D of AB is 0, we cannot conclude anything. The 3 points that I would include on your note card are those first 3. We're not going to have to worry about the last one in our class. All right, let's see how this works. We have an example, a function given in terms of x and y, so it's three-dimensional space. We are going to find the critical points and then determine if they are relative max, min, or saddle points. So the idea is you have to find your partial derivatives. First, we'll find the partial with respect to x, which means we're going to treat the variable y as an actual constant. When we take a derivative of a constant, we get 0. The partial of f with respect to y comes next. In this one, we are going to treat x as a constant and y is the variable. We're also, at the same time that we're taking these derivatives, we'll go ahead and find the second partials. So find the second partial of f with respect to x both times. And then let's go one more step. What about the partial of f with respect to x and then y. This is your second partial derivative. We don't have any we don't have any y terms in our function that is back here. This function right here is what I'm looking at. We don't have any y variables, and so that means that everything we have is a constant, in which case its derivative is equal to 0. And then finally we need the second partial of f with respect to y twice, and we get just -6. The next thing we want to do is find the critical points, and this is done as was described above by setting both of your first partial derivatives equal to 0 and solving that system of equations simultaneously. And so the system of equations, 4x plus 4 equals 0, as well as -6y equals 0, is what we have to solve for both x and y. The first equation, it's not too hard. We see x equals -1. The second equation, we'll get y equals 0, and therefore your critical point is -1, 0. And now we need to decide if that is a max-min or saddle point. We're going to do that by constructing your d-test formula, which is d of xy. And d of xy, remember, you highlighted it maybe like I did on the screen, is found by taking the second partial with respect to x times the second partial with respect to y minus your mixed partial squared. So go back up to your formula and understand where each of those pieces are coming from. There's the first, there's the second, there's the third. We simplify this. What do we get? -24. This is a negative number that is less than 0. So go back up to those points that we highlighted, and it tells you that if the d of AB is less than 0, which it is in this case, no matter what I use for the values of x and y, it doesn't matter. We're always going to get -24, which is negative. That tells you that your critical point, -1, 0, is a saddle point. And that's it.